Okay, so let's take some questions that will further explain the existence of Fourier series or the condition. There is a question. Can the function f of x equals 1 over x minus 2 at the domain of 0 to 3 be expanded in Fourier series? Can the function f of x equals 1 over x minus 2 and the condition x between 0 and 3 inclusive be expanded in Fourier series? Okay. So now the first thing is that you have been given the function f of x is equal to 1 over x minus 2. The second thing is to look at the condition. The condition is this. Now, let's check whether this condition will make this finite and defined. Now, I realize that looking at the nature of this, if I put 2 here, I'm going to get 1 over 0, which is infinity or math error. So I will say that at x is equal to 2, we have f of x being equal to 1 over 2 minus 2, which is infinite. At x is equal to 2, f of x becomes infinite. So we conclude that, that f of x has discontinuity. F of x has discontinuity at x is equal to 2. Meaning that we can't continue, there's no continuity at x is equal to 2 because there's a break-in. Okay, so that is how a problem like this is solved. This one is explaining the conditions for Fourier series to exist. So let's pick another question. Now, let's pick a question of this form. Can the function f of x is equal to 1 minus s squared over 1 plus s squared be expanded in Fourier series? Can the function f of x equals 1 minus s squared over 1 plus s squared be expanded in Fourier series? Okay, so let's answer this. So the first thing is that it must be, if you remember the condition, it must be single valued, it must be defined, etc. Now, so f of x is given as 1 minus s squared, 1 plus s squared. Now, the first thing to consider, here they did not give us any condition. Looking at the question, they didn't give us any condition as compared to the first one that has a condition. So if this one doesn't have a condition, it means that it works for all real numbers. So we can say that f of x is defined for all real numbers. So we can say that every number between positive and negative infinity, it will never give us math error. It will never give us infinity. Because there's no value that of x that when you put inside this, you get math error. When you put x is equal to 0, you won't get math error. When you put x is equal to 1, you're not getting math error, etc., etc., etc. Okay, so that is the first case. Let's go to the second case to prove it. He said that, so this doesn't make it discontinuous. So let us investigate the others and see whether completely it can be expanded in Fourier series. Okay. So we move on to case 2. Case 2, let's check the derivative because we said that it must have a finite number of maxima and minima. And anytime we talk about maxima and minima, we know that we have to differentiate, equate it to 0, those things, and find the x value. So what we are supposed to do for a finite maxima and minima for a finite maxima and minima, f prime of x should be equal to 0. Okay, so let us first find f prime of x is equal to 0. So we are going to use the quotient rule since it's a fraction, like a rational function. So 1 plus x squared, we keep the denominator, we differentiate the numerator, minus we keep the numerator, we differentiate the denominator, all over the denominator to the power 2 is equal to 0. We make x the subject. Okay. Or we find x, we solve it and find it. So I multiply through by the denominator. When I multiply through by the denominator, it goes here to become 0. Then the top one becomes minus 2x cubed. We expand this one, minus 2x plus 2x cubed is equal to 0. I've multiplied through by this. Okay, I can see that this will cancel this. This and this will give you minus 4x is equal to 0. Then we have x is equal to 0. Now, at getting x is equal to 0, we say that it has only one extreme value. You know, x is equal to 0 is an extreme, is a maximum value. Okay, and you say it must have a finite number of maxima and minima, or extreme value. In other words, the number of x answers that are supposed to be countable, supposed to be finite. You shouldn't have a lot of x values that are uncountable. Okay. So we can say that with these two cases, we can even go to the third case that says that it is must be really integrable. Okay, meaning that within infinity to infinity. Meaning, for example, we have case 3. Let's say it is absolutely integrable, absolutely integrable between this and that. And we get the condition for absolute integrable. It says that we can integrate between negative infinity to this f of x dx. And we have this 1 minus s squared, 1 plus s squared dx. We should be able to integrate this. Okay. Certainly, when you integrate, of course, there is an absolute value sign here, meaning there's an absolute, meaning that everything that is here is supposed to be positive. And this one, you can solve it by saying let x is equal to tan theta. Dx is equal to sec squared theta d theta. Okay, 1 minus x squared will be equal to 1 minus tan squared theta. 1 plus x squared will be equal to 1 plus tan squared theta, which is the same as sec squared theta. Then we have the limits, negative infinity to infinity. And here theta is equal to tan inverse of x. So tan inverse of negative infinity is negative pi over 2. Tan inverse of this is the same as pi over 2. What I'm saying is that if I make theta the subject here, theta is the same as tan inverse of x. So when x is equal to negative infinity, I'm going to have theta is equal to tan inverse of negative infinity. Okay, or negative tan inverse of infinity. Now, what is tan 90? When we were in SHS, we used to say that tan 90 is matter or infinity. So if tan 90 is infinity, tan inverse of infinity is 90. So we have minus pi over 2. So that explains why we have this. Okay, so then we can continue our integration here to be minus pi by 2. Then we have 1 minus tan squared theta, sec squared theta. Then this is sec squared theta d theta. That is using integration by substitution. Okay, 1 minus s squared is this, 1 plus s squared is that, dx is this. So this and this cancels. Then we are integrating this. So I will have minus pi by 2 to pi by 2, 1 minus sec squared theta is the same as 1 plus tan squared theta. So tan square theta is same as sec square theta minus 1 theta. So the whole of this is the same as integral, negative integral of minus pi by 2 sec square theta. And when you integrate sec square theta, you get tan theta. So this, the whole of this will give you minus tan theta with the limit pi by 2 minus pi by 2. Okay, so you can put it in. When you put pi by 2 inside this, tan pi by 2 will give you minus, we have minus infinity plus infinity, which possibly minus infinity, yes, plus infinity, then, okay, minus infinity, and that will give you minus infinity. Okay, so we can conclude on this and say that it's absolutely integral. We have integrated it, we got an answer to be negative infinity. You know, when I put pi by 2 inside this one, I get tan pi by 2, which is infinity. Okay, so this minus infinity, then minus tan of negative pi by 2 will be plus infinity. So minus, so that will give us minus infinity to give us minus infinity. So these are simple examples. Okay, so let's move on.